bearings SY507M for the housing, YEL207-2F the bearing, SY35WF for the bearing. I'm assuming it's Alton's bearing.
Yep, got this.
Okay. I'm going to cut and paste that. And paste that. Try again. It's a bit strange. It doesn't find something it tells us. Searching.
We have dimensions.
No, we have to go actually browse through the catalogue, okay? So, rolling bearings.
Rolling bearings.
It's a deep groove. It's called a wide bearing. It's supposed to be a deep groove. So go to product table for the wide bearing. I'm saying wide bearings is usually referred to as insert bearings. So basically sealed deep groove ball bearings in 1660 series with convex sphered outer surface. Because it goes in a plumber block, it means that the bearing can move around with it. Okay, here we are, we found them now. Okay, so what was the designation? YL272F, yeah? Okay, so next page, not quite.
Yeah.
Next page. It must be quite a large bearing. Yes. 207-2F. Okay, so we have that. Okay. What we have is the diameter one, which is the diameter greater than the bore, essentially the depth of the, I don't know what you call that, the inner race of the bearing, is 46.1 diameter, okay, and we'll save this as a PDF again.
46.1.
So the PDF doesn't seem to actually include the drawing. Yes, it's 46.1 taken from the actual diagram. It's okay, as long as we know where we can find things. Okay, so that diameter is 46.1. That's
okay. So that would be the minimum we need. Is that?
I think that would be the maximum.
Maximum.
Yeah.
So is that the stop?
I would make the step that size. I'd make the step the same size as that race.
Can it not be bigger?
I think the problem is when it gets bigger is it might impinge upon the housings.
Right. So if we keep it maximum 46.1.
Yes.
Right. So if I put.
So 46.1 for the largest.
Less than 46.1.
Yeah.
Oh, cool. Yeah.
Okay.
Yeah.
So what do we drop down to there? I mean, I suspect it may make sense at the very end is to drop that down to 35 as well.
We can try that, yeah.
Because what we want is between, well, what's halfway between 25, which is the bearing and that diameter.
35 is a good.
That's about 35 because it's around 20 difference.
Yeah, because we need to iterate this.
We need to, so we start with
So
35,
we can try
okay?
for 35.
Now at that end,
the motor end,
we make it,
25.
I suppose we make it the change as small as we possibly can.
Yeah, we have 35 on one side.
Yeah. I think we go to 25 because that's what we have for the bearing, the step for the bearing at the other end.
We tried that as well.
To 25. So we go essentially 25, 35, 45, 35, 25.
Okay.
Because we keep it as a 46.
Yeah.
Okay. So now what we need to do is we need to work out. We're going to create an Excel spreadsheet. Yes. I think is the easiest way to do this because this will involve iteration. Okay. Now I'll save this as a spreadsheet as.
Put the file name here.
On the desktop as year 2 design stress calc. Okay,
yes.
That's an Excel spreadsheet. So what do we need as entries? Well,
we need to decide
diameter.
The nodes.
Yeah, what the nodes are.
There's an example table here.
Okay, okay. Right,
so the notes are where the
example of what we can have. We need a diameter, a vertical bending moment MV, a horizontal bending moment at that node MH, and MC, which is a combined.
Combined, yeah.
Okay. Now, I don't know the way it's actually laid out. We can keep it. That's just simply to do with bending.
Yes.
Also, we have to consider when we're looking at stress, what's the torque basically?
Yeah,
what's
just
the
that will give
torsional
you
stress?
The torsional stress.
Yeah.
And I think there was
We're not looking at shear stress.
no,
No, I
but there
think
was
there was a note to the effect here.
to say
In shafts of power transmission, the direct stress due to bending and the shear stress due to twisting are usually the critical factors.
yes. So we, based on this rationale,
Yeah.
we are going to try and not ignore
We're ignoring shear stress.
shear stress.
We're just taking bending and torsional. Okay.
Yes.
So I'll put torque in as well as one of the entries to the spreadsheet. We need to know the second moment of area and the polar moment, I and J basically, the polar moment. So we end up with
Then we can calculate
the bending stress and
torsional stress,
Now we have an equation,
or combined stress.
combined stress. It's not as simple as summing them.
It's it's principal stress based on
Principal
maximum
stress.
shear
Yeah.
stress theory.
Yeah, phi x upon 2 squared plus torque squared.
All square
Square.
brackets square root.
Yeah.
Okay, so this is the equation we're going to use.
Okay. Right. Okay.
So
Right.
do I,
If I just quickly pop back to see what other. So what actually you're saying is that we're going to have the combined stress at that node. Then what we need to do is just say what's allowed.
yes, but then what are the notes? The notes will be where the critical
Yeah, at the shoulders.
stress is, where the
On the
shoulder is.
shoulders.
So we have 1, 2, 3, 4 notes, but also we need
I mean, we can have another node at the midpoints of the pulleys, perhaps.
yes, where the loads are applied are where the critical stress
Yeah.
is as
So
well.
do you want,
So yeah, we have 5 points, yeah. So point 1 at the motor pulley.
so you want two at the shoulders as well?
This shoulder here.
Do you want to work out the shoulders at the midpoints of each?
So you have
Are we going to
One at
assume
the
all
left
of the
one.
loading goes straight through the midpoint? For example, for a pulley,
straight
it
to
goes
the
straight
step.
through the midpoint of the pulley in terms of the length.
right,
But then we have a shoulder.
but the pulley is located
Yes, so the midpoint
at
of
the
the
step.
pulley. Well, the midpoint of the pulley isn't at the step. The end point of the pulley is at the step. Are we going to calculate both at the step and at the midpoint? Assume that the loading goes through the midpoint. I mean, so would it be uniformly distributed load over that area? I'm not sure how to deal with that.
The only thing that might affect is the closer you are to the step, this stress concentration effect.
Yes. I mean, the worst case is probably to assume the loading goes through the step. It'd be the
Yeah,
worst case,
Wouldn't
won't
that
it?
be
So if we take the 4 nodes at
at
the
the step?
steps and just assume that
The
anywhere we're
loads
talking
are
about
applied.
loading, it's acting at the end point. So, for example, the end point of the bearing against the step, the end points of the pulleys
Yes.
against the step. That's the worst case, isn't it?
Okay.
So take node
So
1 as being
put one at the step where the motor pulley
the motor pulley is, yeah.
meets the step. Yeah.
Yep. So I can
Okay.
start entering these, okay. Because we have stress concentration factors we have to consider for these afterwards. Now, if I could perhaps start entering the diameters. So the first iteration we have 25 diameter at node 1,
Yes.
35 diameter at node 2, and
Node
also
2.
essentially at node 3. The larger diameter will only be. Is it worth having just for that one section? 'Cause, one thing I'm concerned about is the torque only acts between the elements between the motor and the pulley. Yeah,
The torque.
the torque.
Right.
For example, at point at bearing B, there's no torque. It's not transmitting anything. It's not in torsion, shall we
Mhm.
say, at that point, apart from if there's an oil seal or there's friction in the bearing dragging it, but that's negligible from this perspective, I'd argue.
Yes, I think we have to assume it's uniform.
Yeah. What I'm wondering is there something
Although
to
there'll
say
be twisting on the shaft.
it may be worth having extra nodes at the midpoints of the shafts just to make sure they're not, because there'll be no stress
Because it's quite
concentration.
long.
Yeah,
Quite long.
yeah, there's no stress concentration factor there.
Do you want to try that as well?
Shall we put that in? Yeah.
There's no